Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is practical considerations for low resistance testing. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Our presenter today is Samir Kulkarni, Applications Engineer. Also, to assist with the question and answer session, we will have two panelists joining us today, Voldy Naranjo, Applications Engineer, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Samir.
Good morning, everyone. Welcome to the special webinar series. My name is Samir Kulkarni, and we are going to discuss the topic of practical considerations of low resistance testing in today's session. So let's dive into the agenda real quick. So we are going to define what a low resistance value is, and we'll understand why we measure that low resistance. What are the different measurement methods that are involved? Then we look at some test recommendations and some challenges that we come across during this testing. And then we look at some applications and some product portfolio, and then we'll end with summary. So let's begin. What is a low resistance? So a resistance value that's typically below 1 ohm is called a low resistance value. Now, where do we find those low resistance values? So one of the key industries would be the electrical infrastructure industry, and that's spread out across so many applications. So for example, if you're in component manufacturing, say you are a manufacturer of motors or cables or switchgear, you're going to have connections that require a low resistance value. Moving on, if you have battery centers or in data centers like battery banks that are connected with UPS systems, you would need a low resistance value between each cell of the battery bank. Next is going on to wind turbines. So several steps in the manufacturing and commissioning process of wind turbines require to have low resistance values. And of course, applications such as railway. And there are so many more applications that require low resistance connections. So why do we make this low resistance connection? What is driving us to do that? So at the center of the screen, you can look at some of the factors that can affect resistance values. For example, contact degradation. Suppose the amount of surface area of the contact is not sufficient, and that's going to lead to a higher resistance value. Then you could have chemical corrosion. For example, if you have a battery that's somehow leaking through its post, and that acid will react with the post and lead to chemical corrosion. Next is temperature. In cases where, say, you have a circuit breaker that has been overloaded for a finite amount of time from its normal rating, so that's going to lead to a temperature change because of I square R losses, and that's going to change the resistance value. Now, the next two examples of loss of torque or vibration can sometimes go hand in hand. Say, let's consider you have a motor that's coupled to a pump and that's feeding a particular process. So because of the vibration that's transferred from the pump to the motor, you can have some of those connections become loose, or they can have a loss of torque situation because of that vibration, and that could lead to a resistance value that is not low enough. Now on the outside ring, you can see some key effects of not having a low resistance, right? Let's start at the very top. That talks about increased resistance of fault path. So if you have a grounding system, be that in an industry or a refinery or a plant or any of that matter, or even out in the power system, in the power grid. So you have grounding systems designed to specifically ensure safety for personnel and equipment, such that if there's any fault, that fault current will pass through your fault path. And in case of that fault path having a higher resistance, the fault current may not flow through that fault path, thereby endangering equipment and sometimes personnel. The next would be hotspots. So because of contact degradation or because of not enough surface area, you can have hotspots generated that will degrade your equipment. The next would be loss of efficiency. So that can happen because of changes in temperature, and then now you're not able to conduct as much electricity as you would before. Now, there are extreme cases where a high enough resistance value is going to lead to cyclical heating, and that heating will damage contacts and any surrounding insulation of electrical equipment, for example. And that is basically not the favorable situation where you want to be in. And low resistance values, when they're measured, they can be trended over time. And once you see unacceptable changes or increases, you can have your maintenance crew come in and perform work on it. So that's how you can drive your maintenance strategy and be in a predictive space where you have more control over situations. So now let's move on to the different measurement methods that we have. So the first one, let's look at a two-wire method. So this two-wire method is generally used to measure resistance values between, say, 10 ohms to about 10 mega ohms. And typically you can use a multimeter, as you see here, to make those measurements. And that's used for general assessment of a circuit, sometimes also called as continuity readings. And it is important to understand here that the value that's measured using the two-wire method will include the resistance of the lead wire and the contact probe resistance. And why this is important is because if you want to measure a low resistance, the two-wire method may not be the best because it has the lead wire resistance and the contact probe resistance. Now, if you're measuring, say, a resistance value of 100 ohms, right? And if the lead resistance and the contact probe resistance, the total adds up to about 10 milliohms, right? So that 10 milliohm value may not be significant enough to affect your final reading of 100 ohms. However, in the low resistance spectrum of resistance values, that 10 milliohm might completely skew the reading that you're trying to get. So let's look at the next method. The next method is the three-wire method. This method is typically used when a very high resistance value is to be measured in the mega ohm range, above 10 mega ohms. And this method is used for what we call as insulation testing. And although insulation testing can be performed with two wires, it is very important to understand the use of that third lead, which is also called as the guard lead. So in different types of electrical apparatus, you could have situations of surface contamination, and that contamination can be cleared out, or that can be guarded, or that can be excluded from your resistance measurement. But case in point is that this three-wire method is used for larger resistance values. Now let's go to one of the main method for measuring low resistance values. That is the four-wire method. So this method is utilized when we are trying to measure a value below 10 ohms. And the key aspect of this method is that we use two current and two potential probes. And this eliminates any errors due to lead and contact resistance. So let's look at that on the picture to the right of your screen. So when you say you have two current probes, you can look at to the right, you have a current probe C1 and C2. Similarly, you have two potential probes P1 and P2. So let's understand how that four-wire method works. To the right side of the screen, you have a quick block diagram of a low resistance tester. So on the top, you have a constant current DC source that's going to inject direct current into your test specimen. Next, you have the measuring circuit, and below that, you have a DC voltmeter that is going to measure the voltage drop that occurs due to the passage of the current. Now, once you understand what the voltage drop is, and once you know what the current value is that you have injected, then the measurement circuit will calculate the resistance as voltage over current. So as you see here, you would use your current probes to inject current. Your potential probes would read or measure the voltage drop that's been generated because of that current flow. And then you'd have the resistance value that's measured. So let's look at test recommendations. Now we understand that there are different methods of measuring resistances, and we are using the four-wire method. So in that, we know that it's important to decouple the current probes from the potential probes. So now that we have that figured out, how do we place these probes and leads correctly? So as you see here, the ideal current connection will inject current above the potential position. So let's talk about that for a little bit. As you can see on the right side of your screen, you have your current probe denoted with the letter C and your potential probe with the letter P. So you can see that the current probe is above the potential probe. And we'll understand that why. That's because you do not want the measurement of the voltage affected because of the current injection. So for example, if you had a situation where you have this arrangement in the center of your screen where your potential probe is connected to your current probe. Now this is obviously the wrong method because what's happening is the potential probes are measuring the voltage that includes the contact resistance of the current probe. And this pretty much makes the whole attempt of measuring a low resistance futile because that measurement is now it's corrupted because of the contact resistance of the current probe. So the whole idea of decoupling the current and the potential probes is not valid anymore. So for that, you have to ensure that you maintain that decoupling of the current and potential probes. You have combined current and potential probes. What that means is you can have the current and potential probes in the same package, but they are different. They're wired separate, but they are part of the same package. Next, you have separate current and potential probes. So in case you are testing different applications where you would need the current and potential probes to be separate, then that would be a good application for using separate current and potential probes. So let's look at situations when the measurement points are close to each other. So in those situations, you use Kelvin clips or C-clamp connectors. So the feature on that is that the current and potential leads are 180 degrees apart. So this allows for the current and potential leads to be close enough to each other such that the measurement is not affected, but they're 180 degrees apart. So you are not measuring the contact resistance of the current probe. So you're getting a more accurate value. So now that we understand how to place the probes, let's understand a little bit deeper on what uniform current density, what kind of a role it plays. So as we know that placement of probes is really crucial to ensure that you get accurate resistance measurements. Remember that the current probes should be outside of the potential probes, right? So this positioning of probes will allow for the test current to flow more uniform. The density of current will be more uniform because of the positioning of these probes. And in case this method or this ideology is not followed, the result is that the resistance values that you would get will sometimes include contact probe resistances or any other resistances that might be in that wrong placement, and that will affect your resistance value. So the ASTM standard B193 talks more information and gives guidelines of how those measurements can be made such that uniform current density is established. Next, once we understand now that this concept of uniform current density, let's look at some common conductor types. Let's say you have wires or conductors that have cylindrical cross sections. So for those situations, your potential and current leads should be separated by a distance of at least 1.5 times the circumference. So you can see on the right side of the screen, if say this is a piece of wire, and you can see that the C1 and P1 lead, and similar to the C2 and P2 lead, they are separated. Each of them are separated by 1.5 times the circumference. And by using this methodology, you can ensure that the current density across your test specimen is uniform so that you get accurate measurements. Next, you have conductors that have rectangular cross sections, for example, like a bus bar. So for those kind of conductors, your potential and current leads should be separated by a distance of 3 times the width of your sample. So on the bottom right of your screen, as you can see, this is a rectangular piece of, for example, bus bar. If that has a width of W, the distance between the current probes and the potential probes as seen here is 3 times that width W. Next, let's look at some industry standards that talk about low resistance testing. So as I mentioned before, you have the ASTM standard B193, that is the test method for resistivity of electrical conductor materials. Now, going on to the IEEE side, standard C37.09 talks about test procedures for AC high voltage circuit breakers rated on a symmetrical current basis. And that standard talks about an important aspect that we are going to look at in this session is test current. So IEEE C37.09 recommends that the minimum test current be of about a magnitude of 100 amps DC. However, this current should not be greater than the rated current of that circuit breaker. Now, if you look at IEC standards, you have the 62271-100 that talks about alternating current circuit breakers. So the IEC standard recommends the test current to be at least greater than 50 amps DC, but not more than rated. And lastly, one of the standards is the NETA acceptance testing and maintenance testing specifications. So the NETA specification talks about comparing your measurement with other phases or similar connections, and those comparisons should not exceed 50%. What I mean by that is, for example, you're testing the phase A as an alpha on a motor termination cabinet. And if that resistance value is, let's say, 100 microohms, so the things that you would do to ensure you've got a good value would be compare it to the other phases like the B phase or the C phase. They'll give you an idea of what those resistance values look like. Or you can use similar connections to make the same comparison. And this comparison should not exceed 50%. So let's look at modes of operation of a low resistance tester. So here we have the manual mode. In the manual mode, you have current that's applied in the forward and reverse direction. So as you can see on the right side of your screen, the picture has a bidirectional arrow. What that shows is that the test current is applied in the forward and reverse direction. Once that current is applied and the voltage value is measured, the resistance is calculated and the average value of the resistance for each direction is then displayed. And why is that done? So before we go into that, let's look at the current and potential leads have to be connected before pressing the test button. And why do we make bidirectional measurements? That's because if there are any junction EMFs generated due to dissimilar metals, those junction EMFs are accounted for when you make bidirectional measurements. So if you have a bimetallic strip that is made of aluminum and copper, a junction EMF because of the electronegativities of both those metals will be accounted for when you make bidirectional measurements. So the next mode, we're talking about the automatic mode. In the automatic mode, your test will begin as soon as the current and potential leads make contact with the test object. So if you're testing a motor termination, for example, for low resistance values, the moment you connect your current and potential leads, a measurement will be initiated. This measurement, again, like the normal mode, is bidirectional. So it will pass current in the forward and the reverse direction. And if you're completed with that measurement and you want to move on to the next phase or to the next item, you can remove the leads and reconnect to make new measurements. For example, if you're testing bus bar for different connections and ensuring that they need to have low resistance values, you can have the current probes connected at each end, and then you can go across different types of connections that you're testing by just connecting the potential leads. Then you have an automatic measurement. After that's done, you can move on to the next section of the bus bar while you can still leave the current probes connected, and then you can use the potential probes to disconnect and reconnect. The moment you reconnect, a new measurement is going to be initiated automatically. So moving on to the next mode is the automatic unidirectional mode. So in this mode, the test current is applied in only one direction. This can sometimes speed up measurement. Say, for example, in intercell connections for battery banks, you can get quicker, faster measurements. However, it's important to understand that the unidirectional mode needs to be applied to the correct application. If you have situations where you have junction EMFs, as we saw before, due to different metal connections, those EMFs may be ignored. So there is always a different operation mode of the low resistance tester that you can use to ensure that those issues are addressed. The next mode is the continuous mode. So in the continuous mode, repeated measurements are made at a 3-second interval of the sample that you're testing. The current and potential leads are connected prior to initiating the test. And this method can be used for continuous monitoring of a surface. So once the leads are connected and once you initiate the test, a continuous measurement is made every 3 seconds and the value is displayed. As you can see with the bidirectional arrow to the right side of the screen, those current injections are also bidirectional. The next mode is the inductive mode. So in the inductive mode, a unidirectional current is passed through the sample continuously. Now, this can be looked at for small motors or small instrument transformers. And because of the inductive nature of loads such as small motors and small instrument transformers, it's important that the voltage that's generated after the current is injected has to stabilize. After the voltage has stabilized, repetitive measurements are taken until a true accurate value is obtained. So it's very important to understand that the inductive nature of such kind of test specimens leads to voltage fluctuations, and that voltage fluctuation has to stabilize, and then the measurement has to be made. Now that we're talking about inductive mode, it is important that the energy that's stored in such inductive loads, no matter how small, no matter how big, has to be discharged. So we have the LED lamp that will flash at the end of a test, and that lamp flashing will indicate that the stored energy in that inductive load is discharging. And once that energy or that current has decayed to less than 1 milliamps, the lamp will not flash. That means the specimen is safe to reconnect. So now we understand what the different modes of operations are. So let's talk about safety. Low resistance measurements are almost always made with an asset out of service. It's almost always de-energized. And that is why the testing instrument should have circuitry that will detect any floating voltages on that test specimen, and it should interrupt the test. Why? That's because high floating voltage can be hazardous to the user and the instrument itself. And the voltage that's generated or that has to be detected can depend on the application. Say, for example, if you're in a switch yard and measuring resistance values on a circuit breaker versus measuring PCB resistance in a lab on a printed circuit board, right? So the next point is talking about inductive loads. So inductive loads have special requirements to discharge the stored energy during measurement because of the inductive nature, they store energy, and this stored energy has to be discharged. So it's very, very critical that instruments that are specifically designed to handle this energy are to be used in resistance measurements. So I cannot stress this point enough that inductive loads are so important to be measured and so important to be handled in terms of safety, because instruments that are designed to test such inductive loads, such as a power transformer, they have special higher voltage levels at the beginning of the test. This higher voltage level allows the windings of, say, for example, a power transformer to saturate. And after that saturation occurs, these instruments then switch over to a constant current mode, and then they measure the resistance of that winding. Now that the resistance is measured, that energy that was injected into the test specimen has to be discharged. So the instrument now discharges the transformer winding, for example, and the measurement. If this is not correctly performed, lethal voltages can be present at disconnection, and that will jeopardize safety. That is why it is so important to use dedicated test instruments that have this feature of discharging stored energy. So we understand what the modes of operations are, we understand the safety implications. Now let's look at some of the challenges that occur. So the lead resistance, that's the leads that are used to make measurements, can have a resistance value, and this resistance value can limit the maximum current. For example, if the leads are not the correct leads or have damage for any sort, this can lead to the inability of the test device to push the maximum current that it's designed for. Next is connections to work surfaces need to be secure. So if you're measuring different, say, let's look at bus bar, right? If the connections are not secure, the resistance that the test instrument will see is going to be high, such that it may not be able to push all the current that's designated to be tested. And this will contribute to a low signal to noise ratio as well. Let's look at some external influences that can challenge low resistance measurements. So you have electrical fields that can be generated in the vicinity of your test specimen, and that can reduce the sensitivity and produce unstable readings. The next factor is temperature. We know that conductor resistance is affected by temperature coefficients. So that's why it's important that the temperature be documented while making low resistance measurements, because this temperature data can be corrected by the instrument and software for record keeping. And once we have that information, only then will comparable and repeatable measurements be truly possible incorporating temperature data. Next is thermal EMFs. So thermal EMFs are small voltages in the microvolt range that are produced due to temperature variance across resistances. How do you combat that? So that is combated by using the bidirectional measurement process, as we saw before. That will address this issue. Next is contamination of contacts. So in circuit breakers, foreign material can be lodged in the contacts, and this will affect the amount of surface that's available to conduct electricity. Because this surface is lower, the resistance value will increase. And the way to combat that is by increasing the test current magnitude and repeating the test. What that does is that gets the contact surface free of such contaminants. It's also sometimes called as the burn-in test for circuit breakers. The next external influence is noise and induced current. So when you have ripple currents or static voltages in adjacent environments, they can affect the accuracy and result in erroneous readings. It's very critical to understand that the voltage that's being measured using the potential leads, that voltage should be greater than the background noise. Otherwise, the measurement is going to be inaccurate. So let's look at this infographic to the right side of your screen. Let's assume that a resistance of 50 microohms has to be measured. So if you use a test current of 1 amp, the amount of voltage that has to be measured is about 50 microvolts. If the same resistance is measured using 10 amps, then the amount of voltage to be measured is much higher at about 500 microvolts. You can see that with an increase in the test current magnitude, the amount of voltage that needs to be measured also increases. So what that does is that ensures that the voltage signal magnitude is greater than the background noise. Of course, if you increase the test current to something as high as 600 amps, the voltage measurement is much higher, about 30 millivolts. But you have to keep in mind that the test current magnitude has to be selected on the application and the rating of that device. Devices will be suited for 10 amps or 600 amps or 100 amps. But once the rating of that device is understood, for low resistance testing, the maximum current range that is supported by that device should be selected. Now let's look at some low resistance testers. They're spread across pretty much the entire spectrum of resistance values and current ranges. So from the left to the right, from the left you can see you have the 10 amp family with the DLRO 10, the DLRO 10X, the DLRO 10 HD, and the HDX variants. Then if you had to measure inductive loads such as motors or transformers, you have our MTO series, our MWA series, and the track series. And as you move on further, say for higher current applications such as circuit breaker testing, you have instruments such as the DLRO 200, the DLRO 200-115, the DLRO H200, the DLRO 600. And then you also have high current devices, there's the MOM 200, the MOM 600, and the Mueller 200 and 600. So let's look at those real quick. So let's look at the DLRO 10 HD and the 10 HDX. These devices support a test current of from 100 microamps to 10 amps. And the resistance range that they can detect goes from as low as 0.1 micro ohms to about 2,500 ohms. These test equipment have generally 5 test modes that we talked about, where you have the normal, the automatic unidirectional, the continuous, and the inductive. Now for situations where you are in an automatic mode, you can have auto start once the leads are connected, as we saw. They also have inductive mode to test very small inductive loads. And you can select the range of power dissipation in that device. So for example, on the DLRO 10 HD to the right side of your screen, you have two ranges, right? You have the 0.25 watt and the 25 watt ranges. So not all test specimens can have the same power that can be applied to those to make measurements, right? You can have a printed circuit board that's going to have a different dissipation or different amount of energy or power you can subject it to versus a circuit breaker. So that's why you have these two modes. One is the lower power mode at 0.25 watt, and then you have the higher power mode that goes up to 25 watts. Then the device has 100 millivolt immunity to background noise. It is 600 volt protected. It's IP54 rated. It can be charged using an AC source and is battery operated. Now, if you see yourself using the DLRO 10 HDX, that has memory capability. The next device we're going to look at is the DLRO 100. As its name suggests, it puts out test current up to about 100 amps. Its range is again as low as 0.1 microohms to about 2 ohms. It can be used for dual ground testing of circuit breakers. And it has smooth DC output with the capability to ramp up the test current for circuit breaker testing. And that's a really critical point that we'll look at further in this session. It has high noise immunity so that you get stable readings. And for a test instrument that provides 100 amps, it's lightweight. It is IP54 rated for protection against dust and moisture while testing. And it is Cat4 600 volts AC or 500 volts DC. It's safe intrinsically for safe operation. And you can save, download, and delete results in the 100X and the 100H variants. And you can remotely operate and it has Bluetooth and asset result tracking. If you move on further for the DLRO H200, this device is lightweight and a handheld instrument that can support instantaneous current up to 240 amps. This auto ranges from about 1 micro ohm to 1,000 milliohm. It has audible indication for pass fail during a test. It is battery supplied. It's lightweight, weighs 2 pounds. It can be specifically used sometimes for dual ground. It has Bluetooth PC communication, and it complies with latest IEEE and IC standards. And if you want to have data management systems, PowerDB Lite is included so that you can have data management and collection. Among the next products is our Mueller 200 and 600 series. So the Mueller 200 supports up to 200 amps DC and 600 amps DC. Their measurement ranges go from as low as 0 microohms or 0.1 microohms to 999 milliohms. And these devices have true DC such that they have ripple-free current. So that's an ideal candidate for circuit breaker testing. As you can see, they can support dual ground testing. It's fully automatic. It can be remote controlled using your PC interface. It has a built-in thermal printer, and a lightweight suitcase that will withstand impact of water, dust, or sand. The next one is the MOM 200 and the MOM 600. So those devices can support 200 amps for the 200 amp version and 600 amps for the 600 amp version. The MOM 200 has a resistance range of up to 20 milliohms, and the MOM 600 has a resistance range up to 2000 microohms. They're highly reliable, used for manual testing, and weigh about 30 pounds. So we now understand what the different techniques are, what are the challenges, what are the safety limitations, and what are the different devices. So let's talk about probes and leads. In the beginning of this session, we talked about how to place these leads correctly to ensure that you get accurate measurements. So on the left side of your screen, you can see the fixed point leads. These fixed point leads are part of the same package, where you have the current and potential probes part of that same enclosure, as you can see here. And the potential probe is clearly marked so that you can make sure that your current probes are outside of your potential probes. The next lead type is the helical spring point. It's very commonly used in battery applications where intercell connections are to be measured. Next, you have Kelvin style leads. So when you have connection points that are fairly close to each other, Kelvin style leads can be used because the current and potential probes are 180 degrees apart. Moving on from there, you have C clamps. So these C clamps can also be used when the measurement points are close to each other. And then you have terminal adapters. These terminal adapters can be used, they're very popular and can be used to make connections with different leads, as you can see here. And of course, the beauty of all this is that you can use the same test instrument with different types of leads and serve different applications. So the flexibility and the compatibility that different lead types can be used with the same instrument, as you can see here. You have Kelvin style leads, you have duplex, you have the helical spring type, which can be used with the same instrument. And you also have the reel at the top, at the center of your screen, that can be used for wind farm applications and for wind turbines. So now let's look at applications. We understand what kind of concepts are involved for low resistance testing. We looked at some equipment that can be used. We looked at what are the best leads. So let's now try and quote unquote perform a test, right? So here we have a molded trace breaker that's being tested using the DLRO 10 HD. So you can see that the red solid lead that has yellow glow is your current lead, and then your red dotted line with the blue glow is your potential lead. So those are your C1 and P1. And note here that the C1 leads are above the P1 leads, which we have been driving, that's the ideal way of measuring resistance, right? On the same, if you look at the bottom, you have the black lead that's solid with a yellow glow. That is the C2 lead, the second current lead. And then you have the P2 lead with the dashed lead with the blue glow. So let's look at, once you make that measurement, how would you import data from, say, for example, the DLRO 10 HDX? So let's look at how you would perform that. So here, you would go on the PowerDB form, you would click on download data. You can see the measurements that are being made, that have been recorded. So you click on one, or you can click on, hold the shift key and select multiple measurements as well. Then you would hit OK. Once you hit that, the results are going to be injected in the form. You can see test numbers, your test current, forward and reverse resistances, and the average resistances. If you click on test details, you can look at, say, for example, let's see, test number 6 here, right? It gives you the time, the date, what type of mode was used. It gives you the test current magnitude, the average resistance. And if you look at test number 8 here, it gives you those same details as well. But this measurement is in the auto mode, and you have the forward and reverse reading. It also gives you indication of the noise status. Now, as far as applications for circuit breakers, for higher current variants like the DLRO 100, we have the ability to control that device remotely. As you can see on the right side of your screen, this is how the interface will look like. So in that, you have the start test button that will begin your test. Then you have a rotary dial that can be used in the manual mode, and you have the continuous mode. And then you have these different current settings. The one here is the ramp setting, and we'll talk about that just here in a second. Then you have the 10 amp, you have the 50 amp, and the 100 amp range. And you have several test options of which DLRO. It gives you the continuity readings for your LEDs, ensuring that the current lead and the potential lead connections are solid and continuous. So let's talk about ramping. So you see here the current versus time graph, that the test current is applied on the device using a ramp, right? Why is that done? So ramping of test current will include issues of current transformers, such as magnetization due to the sudden inrush of DC current. And this is very critical to avoid any kind of misoperation of differential protection schemes due to such a high ramp rate. So instead of applying the test current as a step change from 0 to 100 amps, instantaneously, the DLRO 100 has the ability to ramp this test current from a magnitude of 0 amps to 100 amps within a finite time. And as you can see on the screen here, that the ramp time has been set to about 1 second. So it will take about 1 second to rise from a 0 amp value to a 100 amp value. So now that we understand the precautions that we need to take for higher current with current transformers, while you're testing breakers, let's look at what dual ground testing is. So high voltage circuit breakers sometimes are grounded on both sides, on the line and the load side. And when you attempt to inject current to measure resistance, because of that grounding on both sides, there's a ground current, and this ground current could affect contact resistance measurements. So that's where you use dual ground technology, and we measure the current that's flowing through the ground loop. Now this current is then fed back to the DLRO 100 in this case, and that will change and recalculate the amount of current that's flowing through the circuit breaker. So let's look at this quick example. So you can see on the left side of your screen, you have a circuit breaker that's grounded on the line and the load sides, and you have the DLRO 100 connected to it. So once you initiate the test, you're going to have the breaker contact resistance and the ground loop resistance, as we saw in the previous slide. So the test current that's applied is going to be split into a segment that will go through the breaker, and the other segment will go through the ground. Now, as you can see, we can measure the current that's flowing through the ground right here with the red arrow, as I'm showing on the screen here. So this current is measured and fed back to the device through the CT. Now, once that current is measured and fed back, the DLRO will recalculate the amount of current that's flowing through the breaker, and this will give you more accurate and stable readings. Now, moving on from circuit breakers, let's look at wind turbines. So wind turbines have several steps where you would need to measure low resistance values in the manufacturing and the installation phases. So for wind turbines, you have lightning protection. So from your wingtip to the base, a low resistance connection is required. And several component parts within the manufacturing process of the windmills will have a requirement of having low resistance. There are several earth-ground bonds on these wind turbines that need to have a low resistance value. And because of the geometry of wind turbines, long test leads are available to make sure that a good and accurate measurement can be made. Next, we will look at cables. So cables can be connected, and in order to make sure that those are connected well, with bondings and interconnections during especially installation, low resistance measurements can be made to ensure that those connections are solid. And if you have cable reels, those cable reels can be used to understand what the length is using a low resistance tester, and you can determine the cable length on that reel. Now, if you have motors, including the railway traction motors, the winding resistance, for example, or low resistance is used to understand what the heat rise is of that motor under load, and then winding resistance can be used to detect short circuit and open circuit conditions. As you can see here, it can be used for different types of commutators, lap and wave windings. So with that, let's summarize what we discussed in this session. So low resistance measurements use the 4-wire method. The key aspect of the 4-wire method is that the current leads and the potential leads are decoupled from each other. So you are eliminating any kind of lead resistance or contact probe resistance by ensuring that you use separate leads for current and separate leads for potential measurement. Next is the type of application. The type of application is going to tell you what kind of a surface you're going to measure. Next is the test current magnitude. As we saw that there are several external influences that can be eliminated or that can be minimized using the correct test magnitude. Remember that the test current magnitude, while higher is better, but we have to keep in mind what the rating of that equipment is to make sure that we do not damage. The next one is instrument use. So we need to understand that what is the right instrument that can be used to measure a particular surface and the instrument that can provide the correct magnitude of test current. And the next feature or the next takeaway from this session is that the measurement type, we had several measurement types that we discussed today. We talked about the normal mode, the automatic mode, the automatic unidirectional mode, the continuous mode, and the inductive mode. Each mode has its special features that can be used for special applications. So it's very important to understand the right measurement type. And finally, you had the leads that are used for measurement. We know that having the correct leads is crucial to ensure that you get the right measurement and you get a more accurate measurement. So to summarize, I would say it's a trifecta of the type of surface you're using, the types of lead selections, and the magnitude of test current. So with that, I would ask Michael to help me out here.
All right. Yeah, of course. Thanks, Amir. So at this time, the presentation portion of the webinar has officially concluded. We'll take a few minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any products. A copy of this presentation, along with a link to the video recording of the webinar, will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next week's webinar, Cable Fault Location with Megger Smart Thumb Digiphone. The presenter will be Marshall Bird. So let's get into your questions. The first one is going to be for Volney. Can low resistance testing be used on DC circuits? 2 examples: solar source circuits of up to 1500 VDC and 10 to 150 amps, and energy storage circuits of up to 48 VDC and 250 amps.
Okay, so I guess the question kind of implies that the circuit is energized. So the very first thing to mention is, well, as anytime you want to run a test like this, you always want to probably work on a de-energized system. And if that's the case, no matter if it's a battery system or a solar system, of course you can use or you can measure this. Now, considering that the system is energized, we talk about the case of batteries, for example. When you do the test on a battery to measure the strap resistances of the battery string, then the battery is going to be, it's an online test, you can use it. And the kind of particular thing on this case is that the current that is flowing through the battery is it's very low. It would be the floating current, and the current that you're using for the test is going to be higher than that current. When you use the bidirectional mode, then the result is averaged. And because the voltages are not too high, then you're not going to affect your test set, or of course you're not connecting across the terminals of the battery. When you do the measurement on circuits with higher voltage, well, considering safety precautions, you could still do the test. If the current value is too high, the current that is circulating through the system is too high, then you may not be able to generate a voltage drop with the instrument that you are using, because the current might be lower than what you are what is already circulating through the system. So in that case, you might need to put or clamp a CT around the conductor that you want to measure, and then that magnetic field is going to generate a lot of electromagnetic force in that CT, and you're not going to be probably to open that CT anymore until that is de-energized. So there are some complications there. So safety, and then the current signal. So that is an interesting application. But in systems with small voltages and small currents, it's something that we do a lot. And for example, battery systems, that's a very common application.
All right, thank you. Daniel, could you provide some clarification on Kelvin clamps?
Yes, good morning, everybody. And I would actually kind of first mention that, these questions we kind of just summarize. We received several questions, obviously worded a little bit differently, but all referring to the use of Kelvin style clamps or leads, and, the distance, the minimum required distance that Samir talked about it early in the presentation, right, coming from the ASTM standard. So that this is kind of a summarized answer, right? So as Amir explained, right, the use of Kelvin clamps is a big convenience for a lot of low resistance applications, right? Testing, for example, contact resistance on circuit breakers, right? Typically, especially when we talk about high voltage breakers, with considerable size, again, the use of Kelvin leads is a convenience, right? And you need to think about the range that, or the result that you're expecting in your application, right? If that measurement is expected to be, let's say, in the milliohm range, I would say it's good to go with Kelvin clamps. When you use these type of leads, yes, you will introduce a small, tiny error, right? Typically in the micro ohm range, right? If you know that just adding few micro ohms to your measurement is not going to impact your results, right, in a negative way, saying that it will be out of spec, again, it will be good to use these type of leads for special applications, lab environment applications, where your measurements will be in the micro ohm range. Obviously, completely recommended to go for the separate leads, right? You having your current and your potential leads completely separate, so you can adhere to that rule of having or respecting that minimum distance for the current density to be good to take the potential measurement. So again, in summary, if your application is, I would say, in the milliohm range or above, good to use or good to go with Kelvin style. Otherwise, go for the separate leads.
All right then. So, Volney, next question. Why is DC current used for measurement of low resistance?
Okay, so there are several reasons. You, of course, you can still or you can also use AC for the measurement. Now, usually AC instruments are heavier. Then the other consideration is that when you do AC signal, then you are not only dealing with the actual resistance, you are also dealing with the inductance or capacitance of the circuit that you're measuring. So you may want only to have your DC value, and although you're just doing a connection to a let's say a splice or a bus bar junction, there might be some values or of the inductance or capacitance that will affect you. So it's a pure resistive value that you're going to get with DC, and it's a smaller instrument as well. Now, depending on what you are interested in measuring, you might need to use AC as well to be able to get that impedance, the total impedance value from the circuit.
All right, thank you. So, Daniel, next question's over to you. Could you please explain dual ground for us?
Sure. So this is a term typically used, I mean, it's not restricted, but typically used when talking about testing high voltage circuit breakers, right? We know that for safety, right, after isolating or part of the process of isolating the circuit breaker is having both sides of the circuit breaker grounded, right? So you can make connections not only for contact resistance, but pretty much in any measurement you want to do on your circuit breaker, you have to make sure it's isolated and grounded on both sides. In the case of the contact resistance test, right? If you're using a typical DLRO, if you leave both sides of the breaker grounded, then obviously that will affect your result, as the current you're injecting will also flow through the ground circuit, right? So in a typical way of test, you have to leave one side of the ground so you can perform the test, and then obviously ground it again to disconnect your leads. Some of our DLROs, like Samir explained, have the capacity of performing the test with both sides of the breaker still grounded, right? So that's what we call the dual ground technology.
Thank you. So our next question is going to be back over to Volney. Do the circuit conductors need to be disconnected from the circuit breaker when testing the breaker's contacts?
So yes, it's preferable because this will be kind of related to the dual ground case that we just saw. So you are injecting current, and what you want that current to flow through the breaker, and not if you're using, let's say, 10 amps or whatever current you're using. If you have a parallel path for that current to flow, or somewhere else that it's going to flow, then you don't want that current to be divided. You want the entire current you're using through your contact, circulating through the contact that you want to measure. So in some cases that won't create any loop for the current to circulate, but if the cables are connected to something that will generate some current circulation and will create a loop, then you want to disconnect those cables from the breaker and just test directly to the breaker.
Okay. Daniel, is there a recommended current when testing windings similar to the recommendations for bus bars?
Right, yes. If I mean, this is coming from the IEEE standard, right? When you're testing windings resistance on a transformer, the range that you want to do is between 1% up to 15% of rated current of the winding. And again, this is coming from an IEEE standard, and it has to do with what Samir explained during the presentation about not heating up the element under test, right? In this case, or windings. And the lower end, the 1%, is so you can be able, so you can inject the current in the winding. So again, between 1% all the way to 15% of rated current of the winding on the test.
All right then. So Samir, you state that the higher the test current, the better. Would a higher test current cause heating of the sample and skew your results?
Yes. So when I said that higher the test current, the better, is that we have to keep in mind what is the normal rating or the normal design of that test specimen. You can have, say, a printed circuit board that may not be handling current in the hundreds of amps, right? So once the rating of that test specimen is understood, within that rating, we should aim for a higher test current magnitude rather than a lower, because as I discussed in the beginning, we have several external factors that can be minimized by using the higher test current magnitude. So the amount of test current that you would quote unquote call high for a printed circuit board is going to be much significantly different than, for example, a circuit breaker. So it is very important to understand the application and the normal rating of that application to choose your test current magnitude.
All right then. So, Daniel, please, if you could explain further on the advantages of having true DC current on CB testing.
Okay, well, I wouldn't say that having a true DC current for circuit breaker testing will be my #1 priority. I'm assuming that this has to do with when Samir covered the DLRO 100, for example, right? If you remember, a couple of the main features of the unit, which is mainly designed towards circuit breaker testing. One, yes, it is the true DC output when operated from the battery source. And second, which I would say is more important, is the ramping of the current, right? This is important because in case you're testing dead tank circuit breakers, when you have those protection elements, right? Your current transformers in the circuit breaker, typically, yes, the circuit breaker is isolated, but those CTs, at least here in the United States, are typically not tested by the same crew that will go and test the circuit breaker. So in most cases, those CTs are still part of my protection system. So if you have a DLRO that would just go whenever you start the test, a sudden increase in current, that might be picked up by the CT and obviously interfere with your protection system. So I would put the ramping above the true DC, but sure, having a clean as possible output of your DLRO will impact accuracy. Right? So yes, I'm not saying it's not important, but I would put probably #2 on my list of priorities for a DLRO when we talk about circuit breaker testing.
All right. So, Samir, how do you know if the measured resistance is correct if you don't have previous data?
So for such cases, and we might find those out in the field quite often, is that you compare that the measured resistance value with similar resistances. For example, you have 3 phases on, you have a motor termination and you have each phase and you get a value for one of the phase. So you would compare it to the remaining phases. You can apply that for almost all AC connections, be it bus bar, cable terminations, circuit breakers for that matter. So that's how, in spite of not having previous data, you can compare that to a similar connection in the vicinity, and you can make your comparison and determine whether the resistance value is acceptable or not.
All right then. So Volney, if we are using the DLRO in a high voltage substation like 400 kilovolts and above, would the DLRO give reading due to high induction?
So depending on the instrument that you're using, the instrument will have a better noise rejection. Also, that's another case where the current level will have an impact. So the induction will probably circulate through the test path that you are trying to measure, and if you don't have a good current level, then you're not going to generate a good voltage drop to be able to measure it. So you want to have good current, a good amount of current, and 100 amps or probably higher would be recommended, and especially in high voltage substations where you have circuit breakers and all of that. So that's probably the level that you start using, or the current level that you start with 100 amps or above. Then depending on the instrument, you might have the circuits or hardware filters and software filters to help you handle that noise induction or not that noise influence. Second or third, you have the grounding. You could have the instrument, a DLRO, or an instrument that is grounded, so that will also help in the measurement. And fourth, I would say if you are having issues with the noise, then you can use the dual ground technique, as it was previously explained. Depending on what you're measuring, you might be able to do this dual ground technique, and that having everything grounded and having the ability to measure with this technique, then you're going to be able to get a good result. So in summary, yes, it can affect the readings, but there are different things you can do to improve your measurement, and you can also have good values in this kind of environment.
All right. So Daniel, when the equipment can measure inductive loads, it can measure the resistance of a transformer without damaging it. Is this correct?
Okay, Michael, I would say this is a very good and important question, and I will spin it a little bit, right? We do have a couple of DLRO models that have an inductive mode, and obviously when you get one, you get through the manual. These modes are meant to test small inductive loads, and right, that also includes small transformers and small motors. And the restriction is it's about not because you can damage the specimen, right? If you're testing a bigger specimen, a bigger motor or transformer, but mainly because two things. And number one, really big, is safety, right? When you're testing an inductive load with this type of instruments, you're pretty much storing energy in that inductor, right? So that means that the instrument you're using should be capable of discharging that energy once the measurement is performed, right? So again, there is a restriction of using DLRs with very small loads, right? If you're dealing with a bigger transformer, a bigger motor, as Amir also briefly covered during the presentation, there are special instruments designed to take those measurements. In our case, our MTO line, right, that stands for Megger Transformer Ohmmeter, can be used on those cases because those units will have a dedicated circuit to discharge, to safely discharge their energy and protect both obviously the persons running the test and the instrument and the specimen.
Thanks. So our last question is going to be for Volney. We have the following applications for measurement low resistance values: ground continuity, circuit breaker contact resistance, disconnect switch contact resistance, bus connection contact resistance. Is there a one-size-fits-all instrument Megger would recommend?
So as it was noticed in the presentation, there are several models of low resistance measurement, and there are different techniques and there are different currents to consider. So and I would say that in the Megger product line, probably the low resistance measure meters are the ones that we have the most. I would say that there's no one fit for everything, one size fit for everything, and this goes kind of related to the type of measurement that you want to do. So for example, for ground testing, it's much better to use a ground tester dedicated for that. Those will need some specific frequencies to work on. That's an AC signal that is generated. Then the depending on if you need a certain accuracy, you would prefer to use a certain specific instrument or some specific leads, and probably having a 200 amp instrument or 100 amp instrument to be try to cover everything might not be good for the applications where you need to measure very small contact points. So it's difficult to cover everything with one single instrument. So it's better to have a different type of instruments for each specific application, and that's the reason why we did this webinar, because we wanted to show all of the challenges, all of the characteristics of the testing, and to be able to understand where you want to focus on the instrument and what you want to select for your application.
Thanks, Volney. So it does look like that's all the time we have for questions. We apologize that we didn't get to your questions today, but we will follow up with you offline in the following week. But I'd like to thank everyone for attending. If you could, please remember to answer the survey. The survey will also include a field for you to request a quote or a demo if you're interested. With that, I'd like to wish everyone a great week. And once again, thank you all for joining us this Monday morning.